Megaphones can produce very loud sounds. A person's hearing can be affected by age and working in a loud environment. Figure 13 shows how the frequency affects the minimum sound level that can be heard by 3 different people, A, B, and C. And we have a 25-year-old who's always worked in a quiet environment, a 50-year-old who's worked in a quiet environment, and a 50-year-old who's worked in a loud environment. Again, this is one of those questions where they've given you 2 factors, right? They've given you people of different ages, so we have 50 and 25 years old, but then also the quiet versus loud environment and how that affects things. So, compare how different factors exactly. So, how does it affect it? Well, first thing's age. So, I would probably write something like the older someone is, the the greater the minimum sound level is. Minimum sound level is, right? Because if you just look at this, the older people just have a higher limit in terms of that. Then so we've done age, and then we're doing the loud versus quiet environment. The louder the environment is, the greater the minimum sound level. Now, you might be thinking, well, that is not 4 marks, and you'd be 100% correct, because there is another factor we haven't taken into account. We've taken into account the sound level, but look at the frequencies. So, for example, with this person here, the amount they can hear goes up really quickly, but then it goes down really quickly if you think about it, because it's the minimum sound level. But it goes down really quickly, and then it kind of tails off. So, for all people, as the frequency increases, the minimum sound level increases, right? If you look for all of them, it all goes up. And then you might say kind of like something about the sharpness of it. So for a 50-year-old, the amount that's worked in a loud environment, it just really takes its toll. You require a minimum sound level that increases much faster. And that will give you your 4 marks. We have bumper cars, and they're designed to withstand collisions at low speeds. During a collision between a bumper car and a barrier, the bumper car and barrier act as a closed system. What is meant by a closed system? It means no energy escapes. And you can also say that there's no external forces acting on the system. It can mean either of those 2 things, so I'll just write them both down to be super duper sure. How does Newton's third law of motion apply between the bumper car and the barrier? It's quite simple, really. As the car applies a force to the barrier applies an equal and opposite force on the car. So remember, Newton's third law is every action has an equal and opposite reaction. Basically, any force that exists will have another force that will act to counter it. So as this car hits the side will then hit the car back, so to speak. That's pretty much it. But during the collision, the change in momentum is 700 kilograms per meters per second. The time taken is 0.28 seconds. Calculate the force on the bumper. So with the change in momentum, you can call this impulse as well. But essentially, that 700 is equal to force times time. So it's going to be, well, force times 0.28. So then the force is just equal to 700 over 0.28. And your job done. So it's going to be roughly 4 times bigger than that. But that's not good enough. Let's just do it a bit nicer. Oh, okay, 2,500. That's nice. That's a much nicer number than I expected. That looks like a W, but I hope you know that that is an N. The bumper car has a flexible bumper. Explain how the flexible bumper reduces the risk of injury. So, the idea between preventing injury upon collisions, and this is also true for things like crumple zones in cars, is that you're increasing the amount of time the collision happens for. So, here's what I'm going to put. Flexible bumpers increase the collision/contact time. because force is equal to the change in momentum over time, this will lower the force acting on the people. That is a perfect answer. So the flexible bumpers will increase T, so make the 0.28 bigger, which means the force decreases. That's why it's safer. For this question, it's going to just be that Suvat equation, that very long and disgusting one. So we have acceleration, distance, and this. So if you try and look in the equation sheet, you have, whoops, I forgot that I'm not writing. V squared equals U squared plus 2AS. So then U squared is equal to V squared minus 2AS. So U is just equal to the square root of V squared, the final velocity squared, minus 2, the acceleration of 2, the distance of 1.5. That's your answer. Again, these calculations, man. It's beautiful. This is actually why I did like physics a hell of a lot in school. Because, I mean, to be fair, the calculations weren't really worth that much back in my day. But I do like this change because physics is all about interpreting math, so it's good that there's quite a bit of maths in it. I know some of you hate math, so that might be why you also hate physics. Cool, we have a Hubble Space Telescope orbiting around the Earth. Damn, it's much bigger than I thought. Just kidding, it's not to scale, of course. What is the name given to objects that orbit a planet? They are satellites. Perfect. Space Telescope uses microwaves to communicate with Earth. A microwave has a wavelength of 12.5, so that's lambda. The speed of microwaves through space. C. Calculate the frequency of the microwave. C or V, by the way, actually. Well, it's just V is equal to F lambda. So if I want F, I'm going to do V over lambda. But remember, our units have to be consistent. So we have meters per second here. We need to change this into meters. So that's 0.125 meters. And that will give me my frequency. For 5 marks. 5 marks. It's just, like I said, man. Physics. It's fantastic. And given that they give you pretty much every equation we've used so far, okay, do I have to give it in standard form? Yeah, of course I do. To change that into standard form, I write the first non-zero number, so that's 2, then a decimal point. Then I write any other non-zero numbers, so that's just 4. Then all I do is I write times 10, and I count how many digits are there after the 2. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. And what are the units? Hertz. In fact, they probably give you the units. Yeah, of course. Explain the effect of the Earth's gravitational force on the motion of the Hubble Space Telescope. Well, depending on how far you want to go into this, but it's going to be circular motion. Because the gravity always acts perpendicular to the direction of travel. Which means it's going to constantly spin around. So therefore gravity acts as a centripetal force. That's it. So it's always going to be in circular motion because as this space telescope goes round and round and round, so it goes round, our force always acts perpendicular to it. So even when the telescope's here and it's moving this way, our gravity always acts perpendicular. And as a result, it's constantly being dragged so that its direction constantly changes, which is circular motion. The Hubble Space Telescope can detect visible light from distant galaxies. The visible light spectra from stars and galaxies include dark lines at specific wavelengths, which give you, by the way, which elements are present or compounds are present inside that galaxy. So this is probably going to be something like hydrogen. In fact, it's just hydrogen. It shows the visible light spectra from the sun and 2 galaxies, and the wavelength is increasing going to the right. Now, if you notice, they're the same pattern, but for some reason, Galaxy A is further to the right than our Sun, and Galaxy B is also further to the right. And they're saying, well, what conclusions is it? What they're talking about here is red shift. So with increasing wavelength, when things move away from you, their wavelength stretches, which means it appears... Well, I mean, no, it's redshift, right? It appears like it's shifted towards the right end of the electromagnetic spectrum. So what conclusions can be made about A and B? Well, A and B are both moving / accelerating away from Earth. The reason for this is the wavelength is increasing. If the wavelength was decreased, then it means that it's moving towards us. That's what we can say about both of them. Now, there's still a difference between them. The difference between them is that A is moving away from Earth faster than B, because there is greater redshift. I would always mention the words redshift in something like this because you can get a mark just for saying redshift. So in a question like this, mentioning redshift is good, but again, those are the two conclusions they want. This is kind of like a little bit extra that you sprinkled in there just to make sure you can get those 3 marks for sure. So, mirror with a smooth surface to investigate reflection. What is the name given to reflection from a smooth surface? It is specular reflection. The idea here is that all of the light is leaving in kind of the same pattern it came in at, as opposed to where it gets distorted out and spread out instead. So here are the results of the person's experiment. So the angle of incidence, and then test 1, 2, 3 with the mean, so the angle of reflection. And okay, it doesn't look like there's much here, but if we look at the angle of incidence and the angle of reflection, the mean, they are identical. So you can say something like the angle of incidence always equals the angle of reflection. And that would probably be the only thing I really say about that. What type of error caused the variation in the results for the angle of reflection? Suggest one cause for this error. So if we go back to his measurement here, it's likely, so if we look here, there is a difference in each of them, right? 8, 10, 11, 20, 21, 20. So there's a bit of variation happening. But why? What might cause that? Well, it's not systematic error. Why? Because if it was systematic error, all of his measurements would be off by a certain amount. So maybe they're all 5 degrees above what you expect. Instead, it's random, right? Like these numbers are just like sometimes above, sometimes below, blah, blah, blah. So it is indeed random error. So what might be the cause? Well, it might be something like misreading the protractor, as in the protractor gets knocked, hands shaky when placing the ray block. Yeah, they called it a ray block in their diagram, right? Ray box even, God. Like that. Something along those lines would have caused that. Figure 18 shows the path of a ray of light through a glass block, but why has refraction not occurred? Because the ray is moving perpendicular to the surface, to the glass. So if the light's slowing down, or speeding up, it's not really changing direction because it's going head on into it. Back to this question, by the way. It's not systematic because, again, the difference, these kind of random variations, they're not systematic, right? They're not a certain number each time. They're different each time. But yeah, so for this, refraction only occurs when you come in at an angle, not if you come in straight on or perpendicular to the surface. Cool. So this is the protractor he allegedly used. When the angle of incidence was 10 degrees, he found that it was 6.0, 6.3, 6.4, and 5.8. But why? So the students should not have recorded these results when using the protractor in this figure. It's simple. You can't read off 1 decimal places. Right? Each one of these is 1 degree. How the hell did he get 6.3? 6 is here. How would you read off 6.3? 5.8, 6.4, how would you read that off? How would you tell the difference between 6.3 and 6.4? It's funny because all of these would round to 6 degrees. So simply put, the resolution of the protractor is not 0.1, it's 1. Hence, readings should have been done to the nearest whole degree. That's why he made a mistake. And again, if you notice, if he read these all to the nearest degree, he would have gotten 6, 6, 6, and 6. That's the problem. Remember, you cannot read a measurement that's more precise than the actual equipment. It's why when you use those meter rulers, the most precise measurement you have is a centimetre. It's not half a centimetre or 0.1. The 30 centimetre rulers, you can read off 1.1 centimetres, 2.5 centimetres, because it shows you that. But these indentations only show individual degrees, not fractions of a degree, not decimals of a degree. Figure 20 shows what happens to wavefronts as they pass across a boundary between air and glass. Simply put, explain in terms of wavefronts why refraction happens. It simply happens because one side, so as the light passes into denser medium, it slows down. One side of the light slows down before the other. So if you look right here, the right hand side is slowed down, but the left hand side is still going in its normal speed. This causes a bending of the light, i.e. refraction. That's the general principle. Because one side slows down, the other doesn't, the actual ray will begin to turn. So the sun actually set whilst I was recording this, just to give you an idea of how long this kind of takes. Anyways, figure 21 shows the transformer. And this, by the way, if you've skipped ahead, this is the difficult question people were talking about because I think it has some, oh my god, it has some crazy stuff in it. So we will get to that, but before then, we have to talk about transformers used to power a lamp using the mains electricity supply. So as you can see, it goes from primary more turns to fewer turns because it's a step down transformer. What material is used to make the core of the transformer? It's called, I mean technically it's just called iron, but you want ideally soft iron. And the reason is because it can be easily magnetized and demagnetized. Because don't forget, that's how we're going to produce that alternating current that we want. That's all. So, determine the current in the secondary coil when the power output of the transformer is 6.9 watts. The transformer is 100% efficient. This means that the power in the primary coil is equal to the power in the secondary coil. So, if you remember P is equal to IV, that means that in the primary coil we have, and that's what we want, right? No, it's the current in the secondary coil actually, sorry. So, oh well, that's easy enough then, isn't it? And the power output of the transformer is 6.9 watts. So realistically, all we need to do is change this to equals IVS. So if we want the current, we're just going to take the power and divide it by the voltage. So that's 6.9 divided by something. Now if we go back, we do have a voltage. And if you look, the way the voltage is going to work, by the way, is in this step down transformer, it's going to drop down in the same ratio that the turns decreases by. So in this case, how many times smaller is the number of turns? Well, if I do 2000 divided by 40, it is 50 times smaller. That means the voltage will be 50 times smaller. So 230 divided by 50, which is just under 5, if that helps. 4.8? I'm going to say 4.6. Whoops. Too easy. Over 4.6, which gives me 6.9. 1.5 amps. For 5 marks? Damn. But don't forget, this also counts as you're working out, so it's not just this. With this one, I actually don't think this question is particularly hard because it is a very standard question. As in, this comes up all the time. It's a 5 marker you can memorize. But cutting all that out, a dynamo is used to generate an electric current. We have this kind of coil thing, a brush commutator, split ring commutator technically, leading to a lamp. And the idea is that the coil begins to rotate and then somehow a current is induced in the coil. Why? Well, if you look between north and south, they're going to be field lines. So, as the coil rotates, the magnetic field lines are cut. Okay? These field lines are cut. This induces a current in the coil because a force acts on the electrons inside the coil. Okay? So the idea here is, as you spin, as you cut the magnetic field lines, a force will act on the electrons inside the coil, which induces a current. And what law is this? That is Faraday's law. Faraday's law of electromagnetic induction. That's it. So the coil rotates and it's cutting the field lines, causing a force to act on the electrons. If you want, you can even add to this like force acts on the electrons into the coil by saying that this accelerates the electrons around the coil, which is a current. This is the definition of a current. Here's the question people started having trouble with. Sketch a graph to show the potential difference generated across the lamp varies for 2 complete revolutions of the coil. Now here's how it works. The potential difference generated is proportional to the speed at which the coil rotates. Now, in this scenario, as I said, the coil will rotate, generating a current, which means a potential difference across the lamp. Now, as this speeds up, there's actually another force, just like Newton's third law says, and another force that will act to oppose the motion because of Lenz's law. So what you're going to do is you're going to have a potential difference that increases, begins to slow down, and goes to 0 as it rotates, and then does the same thing again. The reason for this, as I said, is that as it rotates, there's another force that's going to act to oppose it. Okay? Another thing to consider is this. And this is where I think a lot of students got a bit confused. And honestly, I don't really blame you. It's not the simplest thing in the world. If you look, when it's parallel here, it's not going to cut any field lines because the field lines are going above and below it. But as it rotates and it goes to this setup here, so again you have the south and north here and here. When it's like this, okay, the field lines can just pass over it. No field lines are cut. Yeah? But when it's like this, all of a sudden it's cutting loads of field lines, which means the potential difference increases. So again, as you turn, you're going to increase your potential difference, and then it's going to turn back, so it's going to decrease. And then it's going to turn again and increase, and then it's going to turn and decrease again. So every time the coil looks like it does in this picture, we're going to have a minimum potential difference generated because no field lines are cut. But as it rotates and goes up, you're going to have a maximum when it is perpendicular. So when it's exactly 90 degrees from where it is, that's here and here. Okay? I hope that makes sense. Another way to think of it is it's going to act like a little bit like a sine curve. So, wait a minute. Where did my answer go? Anyways, alright. So it says over 2 complete revolutions. So what I'm going to do is, I'm going to show it like this. I'm going to say 90 degrees, 180 degrees, 270, 360. Oh, I'm not going to have enough space now. But the idea is I want to kind of space it out. And here's what it's going to look like. It's going to look, as I said, so we're going to imagine it is flat. No potential difference because it's not turned yet. Then as it turns, like if you think about it, my hand's like this. My hand, and I've got lines going up and down. As my hand goes up, I'm starting to hit more and more and more field lines. So when it's like this, it's hitting a few field lines. When it's like this, it's hitting all the field lines. So it's going to increase gradually up to a maximum. And then, as it starts to go back down again, it's going to start to decrease again. Now, here's where this gets a bit tricky, right? Do we go into the negatives? Because technically speaking, potential difference is a scalar quantity, which means there's not really a negative involved. But if you do a negative, it is allowed because it shows Lenz's law, which means it opposes it, but that's fine. Then again, we're going to have the same thing approaching again. That is one complete turn. It goes from here, peak, minimum, peak, back round to here to minimum, and it does the same thing again. And I knew I wouldn't fit everything. Damn it. Alright, it should be 2. Put in there. For 1 mark. Yay. So, the last thing is the lamp is disconnected from the dynamo. Why is the dynamo suddenly easier to turn? That is a very interesting question. So here's how it works. The lamp is disconnected from the dynamo. Why does it become much easier to turn? Well, here is what I was mentioning back up here about Lenz's law. So when you have a induced force acting on something, so you have this induced current, there's going to be a current that opposes the current that's induced. So let's say, for example, we've induced a current and it's acting this way. Lenz's law states that there will be a kind of opposite current that will begin to form, which will slow down the spinning of this coil. Now, if I disconnect that lamp, there can't be any current generated, right? Because it's not a complete circuit, which means Lenz's law can't actually happen. So, oh, there it is. Anyways, alright. So, due to Lenz's law, electromagnetic induction induces a current that opposes the change that caused it. Because the circuit is now disconnected, in fact, maybe I should say, because it opposes the change that caused it, it's going to resist the motion of the coil. Why? Because remember, what's causing the current? It's the rotation of this coil. So Lenz's law says that the current will induce in such a way that it will slow down the change that caused it. It will slow down the current. But because the circuit is now disconnected, no current can be formed. Hence, there is no force opposing the motion of the coil. Hence, it is easier to turn. So again, in this normal scenario, as the coil rotates, Lenz's law states that a current will be induced that opposes the change that caused it. So a current will try and slow down this coil. We've now disconnected it. We've disconnected the circuit. No current can be formed, which means nothing's now opposing the movement of this coil, which means it's going to be easier to turn, right? Because there's nothing opposing it, nothing stopping it. Which brings us to the end of this wonderful paper, kind of. I hope you found that useful. Again, people that are doing Edexcel and OCR will also find this useful because these topics are cross the specs. Very interesting paper. I'm glad that I managed to go through it, but if you do have any questions, let me know in the comments and I can maybe help you out. But other than that, best of luck and I'll see you in the next one. Hey guys, welcome back to another video. I hope your exams are going well so far. And if you're watching this in the future, I hope your exams will go well. But I have the 2023 Paper 2 Physics because Paper 2 Physics contains some of the harder topics in GCSE Physics, in my opinion, especially with like electromagnetism, the generator effect, the motor effect, that kind of stuff can get very, very difficult. So I decided to go through this paper. Now I think the paper starts off quite soft, So if you want, you can skip towards the end, but the last question is definitely where I'm going to take you through the exact thought process for the generator and motor effect. So if you want to see that, then just jump straight to the end, I don't mind. But I'm going to go through this entire paper step by step and just kind of give you the exact thought processes and hopefully explain some of the science behind the physics paper too. So without further ado, let's just jump straight into it. Infrared waves are transverse waves. Cool. Complete the sentence. In a transverse wave, the direction of oscillation is blank to the direction of energy transfer. It is perpendicular. This is just the definition of a transverse wave. I don't think there's anything too spectacular about that. Student investigated how the colour of a surface affects the rate at which the surface emits infrared radiation. Now, it should be noted that this emitting infrared radiation means basically how quickly the object cools. Okay? How quickly it cools. Because as you emit infrared radiation, you're giving off heat. That means heat is going from you, or the object, out into the surroundings. So if I'm giving off a lot of infrared radiation, it means I'm cooling down very quickly. That's the idea behind this. The more infrared radiation you emit, or an object emits, the faster you're cooling down. It doesn't mean the colder you are, but it's the faster you're cooling down. Okay? Keep that in mind as we go through this question. So we have a silver-coloured flask. Remember, silver is a very reflective colour, and a black-coloured flask, don't forget, black is a non-reflective colour. In fact, it absorbs all of it. You might be seeing where I'm going with this. And we have a kettle of cold water. I'm assuming we're going to heat this up in a second. The student wrote the following hypothesis. The black-coloured flask will emit more infrared radiation than the silver-coloured flask during 10 minutes of cooling. Describe a method to test this hypothesis. Well, the first thing I like to do is I like to think about, well, what am I actually going to measure, right? So we have 10 minutes of cooling. Okay, that's like a control variable. We're going to fill these flasks with hot boiling water, and then after 10 minutes we're going to somehow measure how much infrared radiation they've given off. Now, there are cameras that can do that, but assuming you don't have an infrared camera, how else can you do that? Well, if you remember what I wrote back up here, the more infrared radiation you emit, the faster you cool down. So in other words, after 10 minutes, the colour that is at a lower temperature will have emitted more infrared radiation, and thus we have our answer. So in this case, they're saying the black coloured flask will be at a lower temperature than the silver one after 10 minutes of cooling. Describe a method. So what are we actually going to do? What we're going to do, and honestly it doesn't really make too much of a difference, but we're going to fill one flask with boiling water. In fact, I might actually want to type this instead because I'm lazy. So fill one flask with boiling water, measure the starting temperature, wait 10 minutes, measure the final temperature, and calculate the temperature change. Repeat for the other flask. The flask with greatest change in temperature is the one that emits the most the most infrared radiation. I don't know why I'm sounding out like this. So that's our method, right? We measure the starting temperature after we've filled the flask up with boiling water. Wait 10 minutes, measure the final temperature. Why do we do that? Well, when you're using a kettle, the starting temperature might be different. Now, here's the problem. Depending on how much you know about science, the starting temperature needs to be the same. I'll explain this in a later part because I have looked ahead to part 3 or part 4, I can't remember, and it will ask us to talk about this, but you need to have the same starting temperature. But this is our overall hypothesis, right? You're going to wait 10 minutes, measure the final temperature, calculate the temperature change, repeat for the other flask, greatest change in temperature. Now, normally with a hypothesis, a method, you might want to include some kind of control variables. So we're going to do things like the time waiting is a control variable, for example. You might want to mention a health and safety thing. So, for example, don't touch the flasks as they're cooling down, because obviously it's boiling water, but something along those lines will get you the marks. Again, whenever you're doing any kind of experiment, chemistry, biology, physics, doesn't matter. Think about what you're measuring and what you're changing. In this case, what we're changing is the colour of the flask. What we're measuring, well, we're trying to measure the amount of infrared radiation. We can't do that directly, again, assuming you don't have an infrared camera. So instead, what we're going to do is measure the change in temperature, which is like a proxy for that. Now, when will the flasks emit infrared radiation at the greatest rate? Give a reason for your answer during the 1st, 5th, or 9th minute. Now, this question seems very weird, but if you think about what's happening, right? This flask is going to be filled with boiling water. They're basically asking you, when is the greatest change in temperature? That's what they're asking you. When is the greatest change in temperature? Right at the beginning, 5th minute and 9th minute. Now, I can't explain this to you in fancy physics terms. I want to explain it to you in terms that you actually might understand. When you order a pizza or when you make a cup of tea or coffee, it goes from boiling to drinkable fairly quickly, right? It cools down relatively quick, but then it stays warm for a really long time, right? Same thing when you order a pizza. When it comes, it's steaming, and then it cools down pretty quickly so you can eat it, but then it stays warm for quite a while, right? It doesn't go cold straight away. This is because the temperature of any object with respect to time will decrease like this, exponentially slowing down, which is handy, of course. It also works the other way around, like if you're melting something. So when something's really, really cold, it will heat up very quickly until it gets to, again, whatever the ambient temperature is, like so room temperature. But that means the greatest amount of infrared radiation will be released in the 1st minute, straight away. And again, think about this the next time you make a coffee, some tea, soup, pizza, your food, whatever. When you first make it, feel how hot it is. Really, really hot. It's going to burn you. Wait a minute, you can then eat it. Wait 5-10 more minutes, it's still warm. Because the rate of cooling slows down exponentially. So what's the reason? It's because you could use the graph to actually explain it. You could probably just draw this graph and that'd be fine. But the idea is that as the temperature of the flask approaches room temperature or the ambient temperature, the rate at which it cools down decreases. That's the fancy science way of putting it. But again, all it is that it's based on the change in temperature. So the difference in the temperature between its surroundings and what it actually is, that determines how quickly something cools. Another student investigated the absorption of infrared radiation by different surface colours. The student filled 4 hollow metal cubes with cold water, each cube with the same side but had a different surface colour. The cubes were then placed at the same distance from an infrared heater. After 10 minutes, they measured the temperature increase of the water inside the cube. What was the dependent variable? So, just as a reminder, a control variable is something you keep the same. So that would be something like the size of the cube. It could also be the same distance from the infrared heater, the same amount of water, etc. The independent variable is what you're changing, which in this case is the surface colour. We're changing the colour of the cube. The dependent is what will change as a result of that. So, or it's what you're measuring. The student measured the temperature increase. So it's the temperature increase. That's literally it. That's all it is. That's all you have to say. Part 5 shows the results. So temperature increase in 10 minutes, we have this matte white, matte black, shiny black. And if you notice, there's a few things. The black colour, generally speaking, increased in temperature more than the white colour, but then also the matte colours increase more than the shiny colours, which is interesting. In fact, those are the 2 conclusions. When they ask you for conclusions, you don't need to say any science. What is the table showing you? Well, there are 2 differences, right? The colour is different, white and black, but also the type of colour, matte versus shiny. So there's 2 things that are different, therefore 2 conclusions, we need to talk about one each. So for the first one, simply put, black increases in temperature. Temperature more than white. Cool. The second conclusion, matte increases in temperature more than shiny. That's it. That's all I have to say. I don't need to do any science there. I'm just reading the table. Figure 2 shows one of the cubes. The cube is filled with water, so I'm guessing through that hole. Yep. So the weight of the water exerts a pressure on the bottom of the cube. Use the physics equation sheet to answer question 0.6 and 0.7. Well, it's on the formula sheet. Area, force and pressure. Well, pressure is just force over area. It's on the formula sheet. Part 7. The water pressure at the bottom of the cube is 1500 pascals. Calculate the force on the bottom of the cube. So again, we're doing pressure is equal to force over area. We want force, so we're going to times both sides by A to get force is equal to pressure times A. If you want the formula triangle, you can also do that. So P, F, A, and then just do a big old triangle like that. That also works, but whatever. And then in this case, we're covering up force, so it's pressure times area, right? Whichever way you want to do it, algebra or formula triangle, it doesn't really make a difference. So the pressure is, of course, 1,500, but do we know the area? Well, the area we do not know. However, it's a cube, right? So the area of that bottom face is actually the area of a square. So what we're going to do is times them both together, which should be, if I'm not mistaken, 0.144 square meters. But let me just double check. It's going to be embarrassing if I get this wrong, because I could have just used a calculator and not had to flex. Ooh, 0.144. Close enough. So, 0.0144. 0.0144. That's it for 4 marks. So the maths in these questions is a lot easier than obviously a maths exam, shockingly. You can pick up a ton of marks just by doing the maths. So do it nice and carefully. You know, do practice it, because it is easy to make mistakes, and these mistakes will cost you. So we have the next question now. This question might be a bit tricky for me to do because I realise it says drawn to scale. So we have an aeroplane travelling. Now I do get what they're going to try and do here. If you notice, they take a bit of a roundabout route. 1 centimetre represents 70 centimetres. Determine the magnitude of the displacement. Now the idea here is they're trying to test if you know displacement. Displacement is not the distance travelled, which would be the length of this line they've drawn here. The displacement is your distance from the starting point. So what you're going to do is you're going to measure a straight line from start to finish. That's it. And now let's say that that's 10 centimetres. It's honestly probably 8 or 9. If I'm just eyeballing this. All you would then do is times it by the scale. So whatever your centimetres is, times it by the scale. So in this case, oh look, I conveniently got 10. So 10 times 70, it's 700 metres. But the idea here is that you know that displacement is literally the direct distance. Even if this was impassable, like it's a mountain or something, it's still the direct distance from the start to finish. That's all it is. We have a nice image of a plane here, and it shows the direction of horizontal forces acting on the plane as it moves in a straight line towards the runway. We have 14,000 newtons of thrust, 9,500 newtons of friction, and 4,500 newtons of air resistance. What's the resultant horizontal force? Now, since it's a plane, it's going to be moving forwards, not backwards, right? Hopefully anyway. So what we're going to do is we're going to basically, you can do this in a few different ways. So you could add up the forces going to the left. So 9,500 plus 4,500, which is 14,000? Yep, 14,000 newtons. And all you're going to do is do the forces going to the right minus the forces going to the left. So 14,000 minus 14,000, which, you know, use a calculator if you need to. Obviously I'm being sarcastic. Is 0 newtons. Don't be afraid about getting 0. 0 is fine. It means the object isn't accelerating. So when a plane is generally travelling, it will maintain a constant speed. So no force does make sense. No overall force makes sense. I did do these numbers correctly. Yes, because add 500 from there, 10,000 plus 4,000, all good. So then it says, describe the motion of the aeroplane as it moves towards the runway. So here we have this 14,000 newtons. This is why they made it 0 newtons, by the way, because the motion is that it's moving at constant velocity. And if you want, you can even say to the right. So in brackets, to the right. That's it. If this number was positive, let's say it was 100 newtons, so we did 14,000 minus 13,000, we got 1,000 newtons, then you'd say it's accelerating to the right. If it was 14,000 minus 15,000, we got negative 1,000, then that means it's decelerating. Okay? Those are just the things that you are thinking of. Air resistance and friction are contact forces. Give another example of contact force. So a contact force is a force where the two objects have to be touching. Okay? So this can be something along the lines of fluid resistance. You can also have drag. You can have the reaction force, the normal reaction force. Things like that. Anything where the objects have to be touching. Don't forget, a lot of forces, the objects don't have to be touching. So for example, gravity. The moon and the earth have gravity towards each other, but they're not touching, thank God. They're not touching each other. There's still a force. With a contact force, the force only exists when the two objects are in contact, when they're touching each other. This is an interesting question. The airplane stops for a short time and then accelerates along the runway. So they are telling us it's accelerating. Figure 5 shows a distance time graph. Now, as you know, hopefully, the gradient of a distance time graph is equal to velocity. It's how quickly the object's moving. So what can we say about the gradient, or in this case, the velocity? The velocity is constantly increasing. So the velocity itself is increasing because the gradient is constantly increasing. Okay? So what would the velocity time graph be? Well, the velocity time graph, there's no velocity until 10 seconds, so we can put that there. But now we need to think of the shape. Well, because the velocity is increasing, then that means obviously we're going to have some kind of increase. Right? Now we can't really tell if the acceleration is changing. So we're just going to leave it as a straight line for our answer. The aeroplane takes off on the runway, so its height above the ground increases. This is how the atmospheric pressure changes with the height of the aeroplane. So as you might expect, the pressure drops as you get higher up into the sky. Estimate the atmospheric pressure when the height of the aeroplane is above the ground is 10 kilometers. So what you're trying to do here is you're going to draw a line of best fit, or a line's probably best. And then all you're going to do, so this is not going to be accurate because I don't have a ruler that works on the computer. If I draw my straight line of best fit, oh, it's perfect. You're going to go up from 10 kilometers and you're going to read off what that pressure is, okay? Again, this is not accurate. This is not the answer. But the idea is you're going to draw your line of best fit. You're going to read up from 10 kilometers, read across whatever that number is. That's your answer to part 6. Again, use a ruler, of course. Don't do what I just did. What happens to the air surrounding the aeroplane as the height of the plane above the ground increases? The density above the plane decreases, the mass increases, the temperature increases, the volume of air below the plane decreases. So if I draw an amazing picture of the Earth, and now we're going to draw a plane, it's going to be a flying sausage, or a turd, I suppose. As you go away from the Earth, the amount of air particles decreases, which is why the pressure decreases, because there's fewer air particles up there. So, which one explains this? Well, the mass of the air above increases would not be true, because the mass of the air below the plane is actually bigger than above the plane. Temperature of the air increases, it doesn't, it actually cools down, but it's not really relevant for this. The volume of air below decreases, no, not really. But the average density does indeed decrease. Remember, density is basically the number of air particles. So, because the number of air particles decreases, the density of the air would also decrease. Simple. If any of you have gone to a mountainous country or are from a mountainous country, like Nepal, for instance, you might notice that when you go to those countries or you go up mountains or whatever, it's harder to breathe because there's literally less air up there. The density of air is quite literally less, which means it's harder to breathe. Now we're getting on to some kind of moments. I love moments. So some cars have a lever that is used to apply the handbrake. This is what the handbrake looks like. The driver applies the force as shown. The force produces a moment about the pivot. And remember, the moment is force times distance. That's going to be really important. How could the driver increase the moment without increasing the size of the force? Well, if you can't increase the size of the force, then what you have to do is increase the distance from the pivot point. This is actually very useful in real life whenever you guys end up using tools. At some point you will. If you hold it further away from whatever the turning point is, the pivot point is, it actually is a lot easier. So if any of you have used a screwdriver, or even a spanner, for example, or an Allen key, where you're kind of putting together that IKEA furniture, if you hold it further away, you have to put in less force, which means it's less painful. So in general, all you need to do is apply the force further away from the pivot. So apply force further from the pivot. So if you'd like, you could even say like further along the lever, if you'd like. The driver releases the handbrake. Figure 9 shows how the velocity of the car changes during the first 5 seconds. So it accelerates constantly, and then it maintains a constant speed of like 15-ish meters per second. Cool. After 3 seconds, the momentum of the car is 24,000 kilograms meters per second. Calculate the mass. Well, physics equation sheet. Momentum is equal to mass times velocity. So, again, if you're using your formula triangle, then we want to work out the mass, which is going to just be mass is equal to momentum over velocity. So what do we need to work out? Well, I know what the momentum is. It's 24,000. What's the velocity? Well, I don't know. What other information have they given me? I've used the 24,000, but they've also told me 3 seconds. So if I look at the graph, if I go up from 3 seconds and read it off, that will be 15 meters per second. So 24,000 divided by 15. Not a chance I'm going to do that in my head. So let's just go, hello, thank you. 24,000 divided by 15 gives me 1,600 kilograms. That is a fat car. 1,600. Wonderful. For 4 marks, man, these calculations, I'm telling you. People hate physics, but the calculation question so far is 8 marks. 8 marks. That's a huge amount. And the calculations aren't that bad, considering you do get most of the equations you need as well. Determine the distance travelled for another 3 marks. That's 11 marks in total so far. Wonderful. So, you can't really use a formula because, well, the velocity is changing, right? It's not just speed times time because the speed is constantly changing. But if you have a look, first 5 seconds of the journey, all we're doing is, if I just get rid of these lines that I drew here, well, how do you get distance from a velocity time graph? You work out the area underneath it. There are 2 ways to do this. So if I block this off, there are 2 ways to do that. Well, 3 ways to do it. One is counting squares. I would not like to do that. The second way is, well, what shape is this? This, my friends, is a trapezium. So you can use the area of a trapezium equation. But what if you don't remember the area of a trapezium question because you're not, that way inclined? Well, you could split it up into a triangle and a rectangle and add them together. Me personally, I do remember the area of a trapezium. Not because I'm a maths teacher, of course, but no, area of a trapezium, which is half A plus B times height. So it's going to be a half what are A and B. A and B are the 2 parallel sides. So that's going to be 5, and that's going to be 3. So 5 add 3, which is 8, but I'm going to put it as 5 add 3 just to make sure you guys are all okie dokie on it. 5 plus 3, but I said 8, which is my bad. 5 plus 3, which is 8. There we are. Times the height. What's the height? Well, the height is the height of the shape. So that was 15. And that's it for 3 marks. Again, I am aware that the area of a trapezium might be an equation you would have forgotten. I mean, I'm hoping because you're doing this exam alongside doing maths exams, you might remember it. But if you want, make it a rectangle and a triangle, same thing, okay? I actually don't think they give you the area of a trapezium in your physics exam, But if they end up doing it, then all the merrier. Times 15. It travelled a distance of 60 meters in 5 seconds, which is... Oh my god. 60 meters. Don't know what I was doing there. My mind is playing tricks on me. Okay, so continuing on the next page. In an emergency, the driver needs to apply the brakes suddenly to stop the car quickly. The driver of the car is distracted. Explain why the distraction will increase the stopping distance. Well, that's because stopping distance is equal to the thinking distance add the braking distance. Basically, thinking distance is the amount of distance you travel while you are thinking about braking. So you see an obstruction, your brain takes time to react, then it applies the brakes. That half a second or so, the distance you travel in that half a second is your thinking distance. So it's the distance you travel before you've applied the brakes. The braking distance is the amount of distance you travel once you've applied the brakes. So, they're saying the stopping distance will increase, but why? The first thing I've done is given a formula, 1 mark. The second thing is, well, which part of this equation would increase? Is it the braking distance? Well, the braking distance is only dependent on the road surface, how fast you're moving, and the quality of the brakes that you have. Okay, well, none of those would change by the driver being distracted, right? It's not like it will suddenly start raining because you're distracted. It's not like your car will change if you're distracted. And it's not like, your brake pads will explode if you get distracted. So it must be the thinking distance. Okay, well, why is that? Well, remember what I said. The thinking distance is the distance you travel before you've applied the brakes. So if you're distracted, will it take you longer to react to something? Yeah. So I would then go to explain what thinking distance is. Thinking distance is the distance travelled before the brakes are applied. Right? In other words, it's like a reaction time. Okay? Being distracted will delay the brakes being applied, hence increasing thinking distance. It doesn't literally make you slower, but it does increase your reaction time. Because if you're distracted, if I'm looking at you and I'm talking, the obstruction's still there, then I look over and I go, oh my god, then I apply the brakes, it takes longer. So, which is also why a lot of people, when they're like on their phones in their cars, for example, they say, well, I'm still looking at the road, but your mind's occupied. So your thinking distance will increase, no matter what. So that's just, anyways, that's another story. Explain why the temperature of the brakes increases as they are used. Friction. So basically, the brakes will grip the tyre, applying friction to the wheels, let's call them, yeah? This releases heat. So effectively, the overall thing that's happening is kinetic energy is being changed into thermal energy. So I know that normally I say 1 mark per point. I would probably just write all of these because it feels more complete. But realistically, just the first 2 points should give you the 2 marks. But the idea overall is that brakes convert kinetic energy of the car to thermal energy through friction. So literally, what the brake pads do is they grab the wheel. That's what they do, they grab the wheel. So there's a lot of that friction, which releases a lot of heat, hence why they heat up, and lower your kinetic energy. A megaphone uses a loudspeaker to amplify sounds that are detected by a microphone. Complete sentence. The microphone is used to convert the pressure variations in sound waves into variations in electrical current. The loudspeaker contains a permanent magnet. Which diagram shows the direction of the magnetic field between North Pole and South Pole of a magnet? Well, all you need to know is that magnetic field lines always go from south to north. So I'm just looking for that. Well, this goes north to south, so that can't be right. This goes south to north, but then north to south, that can't be right. This one goes south to north, good, but then north to south, that can't be right. This one goes south to north and south to north, which means it must be the correct one. Some magnets are permanent magnets, some are induced magnets. What are induced magnets? So, there is a kind of technical definition that you need to be aware of. So, an induced magnet, in fact, let me type it. An induced magnet is a magnet that is only magnetic inside a magnetic field. Okay, so for example, the classic example is a lump of iron. Iron is not really magnetic, so it doesn't behave as a magnet until you put it inside a magnetic field, in which case it is now a magnet. Something along those lines. So they're not permanent, they have to be induced, they have to be turned on, so to speak. Figure 12 shows parts of the loudspeaker in the megaphone. So we have movement in the cone, and if you notice, that movement is going to move the coil into and out of a permanent magnet. Keep that in mind. What is the name of the effect that causes the coil to actually move? Well, so of course the current can cause it to move, but why? Well, you can eliminate the ones that don't exist, right? The speaker effect is not a thing, the electromagnetic effect is not a thing, the induction effect is not a thing, it has to be the motor effect. But not just that, think about, when it's talking about movement, what is movement? It's a motor. So it is indeed the motor effect. Another 4-mark calculation. When the current in the coil is 16 milliamps, the force in the coil is that, the length of the wire, cool. So we need to work out the magnetic flux density, which is given by the letter B. And we have a length, a current, and a force. So that is good old-fashioned F equals Bil, B-I-L. Where B is magnetic flux density, I is the current, L is the length of Y, and F is the force. So if we want magnetic flux density, just some simple rearranging, divide both sides by IL, you get F over IL. But wait, there's more. So we have 0.013 over, now the current, 16 milliamps, you can give it in terms of standard form, but the idea is you need to divide this number by 1,000 in order to be able to actually do this, because the equation requires you to have your standard units, and L is just 6.5. And that right there should give us our answer. 4 marks in the bag. How nice. Fat fingers again, 0.016. Multiply, no, that's multiplied by 6.5. Gives me 5 over 4, gives me 1.25 Tesla, which is actually ridiculously strong, believe it or not. That's it, 4 marks again. I love these calculations.